Right, hi folks. This next section introduces what you need to know about the haloalkanes in the knowledge pack. This is covered in section 1 mostly, but also introducing the reactions of the haloalkanes somewhat in section 2.9 and on into sections 3 and 4. So we will go into mechanisms in some separate little sections. So this is the kind of the basics about the haloalkanes. So what do you need to know? First of all, drawing haloalkanes. Haloalkanes are simply molecules where one or more hydrogens has been replaced by a halogen. So very simple ones. Full structurally, then you just have the molecule, but instead of a hydrogen, you have a halogen, like chlorine. So that would be full structural, simply a halogen in place of a hydrogen. If you're going to do that skeletally, then if you have a chain, obviously you wouldn't normally you don't draw the hydrogens, but you do draw anything else that's attached. So if you have a halogen attached, then you just draw a line to it. Remember, that's not an extra carbon. So if there's something else at the end of a line, if there's something written at the end of a line, then there isn't a carbon there. So this is a 5-carbon chain, pentane, with a chlorine attached to the middle carbon. Shortened structurally, you get things like if a CH3 group, and then if the next carbon has a bromine on it, instead of being a CH2, you just write CHBr. To say that that second carbon has a hydrogen and a bromine, and then the next carbon might be a CH2. And then if there was 2 fluorines attached to a carbon, CF2, and then maybe a CH3 at the end. Like that. I'll just convert this one to skeletal. So this would be the carbon without any halogens going to a carbon with a bromine on it. Going to a carbon without any halogens, and then going to a carbon with 2 fluorines, and then going to a carbon without any halogens. So just maybe pause the video, have a look at those, just see that they make sense to you. Relatively straightforward. Okay, the naming of them, you simply use the prefixes. I think the plural of that might be prefaces, but never mind. We'll say prefixes. Chloro, bromo, iodo, great name, fluoro. No, that's F-L-U-O-R-O, not F-L-O-U-R-O. A lot of people write fluoro, F-L-O-U-R-O, but it's fluoro, like fluorine. And so those go in front of the name like branches, where you've written methyl and ethyl in front before. So I'll give you a couple of examples, then we'll have some to try. So we have this molecule, and let's put a Br here, an F here, and that there. So this one, if you look at the carbon chain, we've got 1, 2, 3, 4, 5, 6 carbons. So it's going to be hexane. There's no functional groups that get named at the end of the name, like alkenes and alcohols and carboxylic acids and all those kind of things. Halogens and the methyl branch all get named at the front of the name as a prefix, not at the end as a suffix. And to get the smallest numbers here, we're going to count from the left-hand side. So 1, 2, 3, 4, 5, 6. That way, if we counted the other way, the fluorine and the bromine would be higher numbers. Yeah, anyway, it would give higher numbers. So the usual rule applies that you put things alphabetically, not numerically. So the bromine will come first, then the fluorine. Well, actually, that is going to work out numerically anyway. So no matter. But it should be alphabetically. So 2 bromo. because you've got a bromine on carbon 2, 3 fluoro, missing the O, try again, fluoro, and then 5 methyl hexane. Okay, so the rules you've learned about naming branches in front of names, you just mix in the halogens with that. So they're just treated like more branches. You add them into the alphabetical ordering. Okay, another one, and I'll just make it a little bit more entertaining, because we like to do that, right? So you might get something like this. Maybe just pause, see what you can make of it. And so the answer here is to spot that down at the bottom you've got a carboxylic acid group, carbon with a double bond O and an OH. That's named at the end of the name and also controls the numbering. So the carbon where the carboxylic acid group is attached is carbon 1. So we're going to go carbon 2, 3, 4, 5, and then remember you can go around corners to get the longest chain, 6, 7. So this is a form of heptanoic acid. And then the other things are numbered and written alphabetically. So the fluoro will come first, so 3 fluoro, and then the 5 methyl heptanoic acid, like that. Okay, another one, you can have multiples of a halogen. So let's go this way, like this, and one up here for fun as well. So maybe pause and have a think about that. It's a little bit of a teaser about following the longest chain. Remember, you don't get sort of branches that are branched or have exciting things attached. Okay, and so you would want to spot that although it's tempting always to go horizontally, the longest chain, continuous chain, that makes sure that you don't have to put oops. Any complicated branches with things attached within the branch would be that. And so we don't have any functional groups named at the end of the name, so we'll just do whatever gives us our smallest numbers, which would be to count from this end: 1, 2, 3, 4, 5. So with 5 carbons, that's a pentane molecule of some description. And then we've got a methyl group on carbon 2, an ethyl group on carbon 3, and then we've got 3 chlorines, on 2 of them on carbon 1 and 1 of them on carbon 4. So alphabetically, chloro comes first. It doesn't matter that there's 3 of them. That's going to make it trichloro, but that's still before ethyl or methyl in the alphabet. So we've got, and this is the bit to pay close attention to, when you've got multiples, you need a number for each of them. So where you've got 2 on carbon 1, that's 1, 1, and then 1 on carbon 4, 4, trichloro. So remember, you need a number for everyone and this kind of multiplier thing, the tri. Then we've got, next is the ethyl on carbon 3. And then we've got the methyl on carbon 2. So that's a good example of how it's alphabetical ordering, not numerical ordering. The fact that the methyl group's on carbon 2 doesn't put it at the front of the name. right at the front. It's after the chloro and the ethyl alphabetically. Okay, right. That's the naming. So do pause and review that if you're feeling a bit uncertain about that. The other thing you need to know for the haloalkanes is the boiling points, and this links to what we've already done a bit of in the intermolecular bonding. So this just reinforces this, the boiling points of haloalkanes. And so what you're supposed to know is that if you stick a halogen on an alkane, so let's say you've put a bromine on, this has a higher boiling point than if it didn't have the halogen on. So just the 4-carbon chain without the bromine, so higher boiling point than that. And so there's two explanations for that. One is that this can only do ID-ID, whereas this does PD-PD as well, does ID-ID and PD-PD. But there's the thing that everybody always loves to forget, the extra detail, that the bromine as big atom compared to carbon and hydrogen, lots of electrons. So you get strong ID-ID forming. So do you remember that? That's the thing, that with lots of electrons in an atom, when they move around randomly, you can get very big uneven charge distribution, and hence large instantaneous dipole and large induced dipole on a neighboring molecule, and hence a strong electrostatic attraction between the opposite charges on the two molecules. So yeah, just notice the multiple features going on there. If you are asked to talk about this, always, show what you know. So you might as well mark on the partial charges. There's the delta plus on the carbon, delta minus on the bromine. So PD-PD is stronger than ID-ID. So with PD-PD, that's one reason why the one bromo butane there has the higher boiling point than just the butane. But there's also, even without that PD-PD, there's the bromine with its many electrons giving us sort of super strength ID-ID as well. Okay, there's more though. You ought to be able to say that if you have this with multiple bromines, that has a higher boiling point than just the one. And the reason, well, pause. Can you think of a reason why that multiply brominated butane, what is that, 1,2,3-tribromobutane, has a higher boiling point than just one bromobutane? And again, you'd want to show what you know, so we can mark on all these pairs of partial charges. It's tempting to kind of go, oh, hang on, maybe they'd cancel out. But to be honest, when you've got when you've got a saturated molecule like that with only single bonds with lots of partial charges, remember that single bonds can twist and rotate. So this molecule is constantly sort of twisting around. They're not locked in a position where they're going to cancel each other out. So there's no particular reason there with a sort of a longer chain like that, why that would be likely to cancel out. So one reason here is that we've got lots of opportunity for PD-PD to form. Whereas this one has fewer PD-PD opportunities. But no, also this one has the whole atoms with lots of electrons, so lots of big atoms with many electrons. And so that's the instantaneous dipole induced dipole explanation again, that with 3 bromines, each of which has many electrons, you've now got lots of electrons in the molecule to move around randomly, creating large uneven charge distributions, large instantaneous dipoles therefore, and that can cause large induced dipoles on a neighboring molecule. Hence you've got a stronger electrostatic attraction between the opposite charges on the 2 molecules, compared to just the one bromo butane. And then finally, for the boiling point, you expected to be able to point out that if you had this, that has a higher boiling point than the similar molecule with like a fluorine attached there. And this one people tend to get wrong because they get very excited with themselves and say, oh yeah, fluorine is the most electronegative atom. So the delta minus on this will be massive compared to the delta minus on the iodine, which although that is a polar bond, the iodine's much less electronegative than the fluorine, so it's going to be not as impressive a sort of partial charge. And it all sounds wonderful, but it's wrong. And so you are expected very specifically to remember that this is a big atom with lots of electrons that can move around randomly. That can move randomly. So we get this very strong ID intermolecular bonding because of those many electrons in the iodine. The fluorine has far fewer electrons to move. Okay, so this is the thing that, you know, although we say PD is stronger than ID and that kind of thing, that when other factors multiply things, ID can come out as a stronger type of intermolecular bonding when something's kind of putting it on, yeah, sort of souping it up in some way. So here the vast number of electrons comparatively in the iodine means that we can get sort of super strength ID. Okay, so that's the boiling point ideas, and then reactions involving haloalkanes. So there's gonna be a fair bit more detail about these reactions, but this is a kind of a just what you need to know in terms of the reagents and conditions and what you can form. So here is a haloalkane. Let's have a bromine. So you need to know that you can make that. So one of the reactions that you'll need to know is that if you start with methane, you can turn it into a haloalkane like this using the halogen. So you would use Br2 and you'd need UV light. And we'll discuss a reason for that. This is a substitution reaction. It's actually called radical substitution. Oops. And you would get HBr as well given off. And then you just need to know 3 things that you can do to haloalkanes, though actually 2 of them are effectively the same. So yeah, this effectively does 2 things, though one of them has kind of 2 ways of doing it. That's a better way of putting it. So one of them is that you can turn the haloalkane into an alcohol. And the other one is that you can turn it into it's called an amine. So 2 ways to get to the alcohol, and then you can also turn it into an amine. Amines, if you do biology at all, you should be familiar with this group from the world of amino acids. Amines have an NH2. Often an NH2 group. We'll learn more about amines as we go on through the course, attached to a carbon like that. So it's kind of like ammonia, which is NH3, but one of the H's has gone and it's stuck onto a carbon instead. So how do you do these? What are the reagents and conditions you need to know? To make the alcohol, heat under reflux. With sodium hydroxide solution. The sodium is completely irrelevant, so just note here all we're actually doing is providing OH minus ions. So the sodium is just, you can't get a bottle of hydroxide ions on their own, so it's an ionic compound. In solution, remember, ionic compounds behave as separate ions, so sodium hydroxide solution has sodium ions in, completely irrelevant, and hydroxide ions that can swap for the bromine. The other way of doing it is heating under reflux with water. Which can also supply the OH for the alcohol. But given a choice, this is slow and this one is much faster. So you tend not to do this and you do this. So sodium hydroxide is a much more useful way of turning a haloalkane into an alcohol. To turn the haloalkane into an amine, this is the weirdest condition you'll ever come across. You react the haloalkane with ammonia. That bit's not weird. And you do that by, you say, heat in a sealed tube. So that you might think, well, what on earth is that? Why don't we just heat under reflux? The point here is that ammonia is a gas at RTP. So there is no point heating under reflux. Heating under reflux has that condenser, the vertical condenser up above the flask. Things that evaporate when the mixture's boiling go up into the condenser, are cooled down by the cold water in the cooling jacket, turn back into a liquid and fall back down into the flask. But if you've got something that's a gas at room temperature, the cold water in the condenser is not going to turn it to a liquid. Even when it, on a cold day, ammonia is still a gas. So you would need a far more impressive condenser to prevent the ammonia escaping. Your condenser would need to have some kind of refrigerant in that kept that had a temperature of like -50 or something degrees C to have any chance of turning ammonia into a liquid. So since the ammonia would just escape out of the condenser, you have to put a lid on top effectively, but then your equipment has the risk of exploding, so you actually need some reinforced tube that is not going to explode under pressure. Okay, this is extra evidence of Marcus's recommendation to you that you do something about your organic chemistry, because you keep on getting new bits, right? You've had the alkenes. There you can react them with hydrogen or halogens or hydrogen halides or water, and in each case you need to be able to say what the products are and the reagents and the conditions. And then we met alcohols and the fact that you can do oxidation of alcohols to things like aldehydes and ketones and carboxylic acids, but you can also dehydrate them to alkenes and do substitution of the OH group for a halogen. And now here we are with haloalkanes, and the fact that you can turn an alkane into a haloalkane, but then you can turn a haloalkane into an alcohol or an amine, all of which will start to look like a hideously complicated load of confusing nonsense, unless you are going to you're taking action to take each functional group and drilling yourself a bit, making some revision resource little posters, sticking it up, quizzing yourself, so that given any functional group, like the haloalkanes here, you can just quickly rattle off, oh yeah, there's only a few reactions for haloalkanes, you can turn them into an alcohol, here's how you do it, you can turn it into an amine, here's how you can do it, and you can make a haloalkane from an alkane, here's how you do it, and then it fits together neatly as some little chunks. Okay, I'd suggest you do a quick review on that. So the key ideas here are you need to know what haloalkanes are. Replacing a hydrogen with a halogen in an alkane, you need to be able to draw that in the different styles and use the systematic naming, which is just an extra sort of branching name in front. You need to be able to predict and explain the boiling points of the haloalkanes using intermolecular bonding ideas, things like comparing alkanes to haloalkanes, haloalkanes with multiple halogens compared to ones with less halogens, and also different types of halogens. And then you do need to know these characteristic reactions of the haloalkanes, and be able to move around freely within that, predicting the product structure, saying how you would make a particular product, giving reagents and conditions, etc.